Okay, so let me go through very briefly what we went through last time and then explain to you why it is that we're going to be talking a little bit more about the statistics of clinical trials, because they're going to figure prominently in how we do some of the analysis of these business deals. So you remember that last time we described a standard randomized clinical trial as a traditional two-armed balanced study. Namely, you have N patients in a control group, N patients in a treatment group, and the idea is that you want to compare the two to see whether or not the treatment has any kind of impact on the patients. And the difference in terms of the treatment outcome is going to be the key focus of the hypothesis testing. The null hypothesis is that there is no difference. So the treatment effect is going to have no incremental impact on the patient's performance. And so the way that that's captured is by the mean, mu, is going to be the mean difference between the two samples. Whereas the alternative hypothesis is that there is a positive effect. And so the question is, how do we choose between the null hypothesis and the alternative? With all of the clinical trials that you will be involved in this industry, you're always going to be looking at those two different hypotheses. You're going to have to keep one eye on the null and another eye on the alternative. So it's a little bit challenging to be thinking about those at the same time, but that's part of the nature of this business. So we said last time that there are two mistakes that we can make in conducting clinical trials. You can either falsely reject a good drug, or you can falsely accept, approve a bad drug. And those are the two different errors that you have to weigh. And the objective, of course, is to be able to minimize all the errors, but we're not going to be able to do that. We're going to have to trade off one versus the other. And the way that we make the trade-off is using the statistical framework of the null and alternative distributions. So we have the sample of our patients under the null hypothesis. That means that we're assuming under the null there's no effect of the drug, but because of patient-to-patient variability, we might get an effect when, in fact, there really isn't any genuine effect. And so the blue distribution is that null hypothesis. It's centered around 0, no effect, but you can see that there's a probability that we're going to get a positive effect, a probability we'll get a negative effect. And what we want to do is to minimize the chances that we will have a false positive, meaning we're going to approve a drug that actually isn't effective. So we set a threshold that says, unless we see data that is statistically significant, we're not going to approve this drug. And the level of statistical significance, that threshold of approval, is this 1.96 threshold. That's the alpha of 5% two-sided statistical significance, meaning that you've got 2.5% in the upper tail, 2.5% in the lower tail. And under the null hypothesis, where there is no effect, the chances that you're going to see a positive effect at this particular level is going to be only 2.5%. So you're going to use that cutoff as the approval threshold. If you see an effect greater than 1.96, it's unlikely that the null hypothesis is true, and that's when you say, okay, I approve the drug. Now, in order to understand whether or not you've got a good clinical design, you need to actually make an assumption about how strong the treatment effect is. And that's where the alternative hypothesis comes in. So the null hypothesis is really there so that you can protect against false positives. You're assuming that there's no effect, and you want to make sure that you don't approve an ineffective drug. But the alternative hypothesis now is where you switch modes and ask the question, suppose I believe that there is an effect. If I believe that there's an effect, and if I use the procedure that I just described, namely that 1.96 threshold, then what's the probability that I will find that effect versus falsely assuming that there is no effect, a false negative? So under the alternative hypothesis, which is this red distribution, now in order for me to draw the red distribution, I need to make a statement about how strong my treatment effect is. In other words, what is the mean under the alternative hypothesis? So in order for me to make that statement, I have to say something about the alternative. And here, I'm assuming that the mean is 2.5. And with that assumption, I can now calculate the probability that I will falsely reject this drug, namely if the value that I get is below 1.96, and under this alternative distribution, it's this area under the curve, that's the likelihood that I'm going to miss out and make another mistake, a type 2 error instead of a type 1 error. So the whole point of clinical trial design is to balance these two. And the key decision that you have to make as a drug developer is how many patients do you want to enroll in your trial? The more patients you enroll, the more likely it is that you can detect this kind of a deviation from the null hypothesis. But of course, the more patients you have, the more expensive it is. So there's that trade-off. And so last time we went through the process of how to calculate all of these quantities with the various different statistical measures. Under the null hypothesis, you can do your usual hypothesis test, calculate a 95% confidence interval, and see whether or not the results of your clinical trial fall outside the confidence interval. If it does, then you reject the null hypothesis, and you've got a significant effect. You will approve the drug, and if you don't, then you won't. So under the null hypothesis, we have a pretty clear analysis for how to go about conducting the trial, and this 1.96 threshold is really what we're looking for in terms of approval or not.